Okay, we continue to learn Chapter 3, Vector Spaces. Section 4, Basis and Dimension. And Part 2, we consider mainly about dimension. So the dimension of vector space, its definition is like this. Let V be a vector space. If V has a basis consisting of n vectors, then we say that V has a dimension n. The subspace only consists of the zero vector of V is said to have dimension 0. This is a trivial subspace of V. Okay. Another trivial subspace of V is itself. V is said to be finite dimensional if there is a finite set of vectors that spans the space V. So this is a finite dimensional space. Otherwise, we say that V is infinite dimensional. We emphasize that the dimension of vector space is different with the dimension of vector. They are different concepts, okay? So for dimension of vector, maybe it's n dimension, for example, n equals 2. However, the subspace, the dimension of the space, vector space, may be smaller than the dimension of a vector. The dimension of vector is 10, the dimension of the space may be only 2. Okay. Now we see some examples of the dimension of vector spaces. On the one-dimension subspace in R3, the dimension of vectors is 3. However, the dimension of the subspace is only 1. So span of X, which equals alpha times X, where alpha can be any scalar. So this set, this space, subspace is only dimension 1, one dimension subspace. However, the vectors here is 3 dimension. Okay, and we can also have this 2D subspace in R3. If X and Y, they are linearly independent, and the span of X and Y with its entry, its element to be alpha times X plus beta times Y, where alpha beta are scalars. So this span of X and Y is a plane spanned by X and Y. The dimension is 2. The dimension of the vector in this subspace is 3. Okay. So R3 is any 3 linearly independent vectors, X and Y and Z. They can span the whole set, whole space R3. So span of X, Y, and Z equals this elements. This type of elements, alpha times X plus beta times Y plus gamma times Z, where alpha, beta, gamma are scalars. So this will constitute the whole space. See? So given you X, a vector X, the span of X is only in this line, okay, dimension 1. And given you 2 vectors which are not collinear, its span is a plane. The dimension is 2. Only 2 vectors. They are necessary to express all the other vectors in this plane. So the dimension is 2. And if give you 3 linearly independent vectors, its span is the whole space. So the dimension of this space is 3. We have this theorem, 3.4.3. If V is a vector space of dimension n, which is greater than 0, any set of n linearly independent vectors can span the space V. And any n vectors that span V must be linearly independent. Okay, let's see the proof. Okay, so the first one, any set of n linearly independent vectors span the whole space. Okay, how to show this? You can see that V1, V2 till Vn be n linearly independent vectors in V. For any other vector V in this space V, the n plus 1 vectors V1 till Vn and add this additional V must be linearly dependent. This is what we learned before, right? If you add 1, they must be linearly dependent. That is, there exists C1, C2 till Cn plus 1, not all 0 such that this equation holds. C1 times the first vector V1 plus the scalar C2 times the second vector V2 plus TL plus CnVn plus Cn plus 1V equals 0. And from here, we can claim that Cn plus 1 cannot be 0. If Cn plus 1 be 0, then there exists C1 till Cn not all 0, such that C1V1 plus TL plus CnVn equals 0. This means V1, V2 till Vn, they are linearly dependent. This is not true from our assumption, because V1, V2 till Vn are linearly independent. So we must have Cn plus 1 not 0. If it's not 0, then we can write V as a linear combination of this V1, V2 till Vn in this form. So V can be written as minus C1 divided by Cn plus 1 times V1, minus C2 divided by Cn plus 1 times V2, and also minus till Cn divided by Cn plus 1 times Vn. Therefore, V1, V2 till Vn span the whole space. See, because your V here is arbitrarily chosen from V. Okay, and now we show the second statement. The second statement asks you to show that any n vectors that span V are linearly independent. So any n vectors that span this space are linearly independent. So how can we find this? Suppose that these n vectors span the space V. If they are linearly dependent, we use contradiction. Okay, if they are linearly dependent, then one of the vector, say Vn, can be written as a linear combination of the others. Therefore, V1, V2 till Vn minus 1 can span the whole space. And further, we do the further procedure. If V1, V2 till Vn minus 1 are linearly independent, we have found a minimal spanning set with size n minus 1 smaller than n. And if V1, V2 till Vn minus 1 are still linearly dependent, we can continue this procedure until we arrive at a linearly independent spanning set V1, V2 till Vk with k smaller than n. However, this result contradicts to the fact that the dimension of V is just n. If it's smaller than the minimal spanning set with size smaller than n, the dimension is smaller than n. Therefore, V1, V2 till Vn must be linearly independent. The contradiction comes from your assumption that they are linearly dependent. Okay, so any n vectors that can span this space must be linearly independent. Okay, now we consider this theorem, which reveals the relation of spanning set and dimension. If V is a vector space of dimension n greater than 0, then no set of less than n vectors can span V. And any subset of less than n linearly independent vectors can be extended to form a basis for V. And any spanning set containing more than n vectors can be pared down to form a basis for V. So this theorem are not difficult to show. Now we consider the standard basis. The standard basis for Rn is like this. So this set contains all the coordinate vectors e1, e2 till en, and R2 by 2, you can choose the standard basis as e11, e12, e21, e22. Only the corresponding entries, one other entries are 0. Remember this vectors, these vectors in 2 by 2 vector space. And for polynomials, for this vector space of polynomials of degree less than n, the standard basis is 1x, x power 2 till x power n minus 1. So these are the simplest basis and most natural to use. But sometimes they are not the most appropriate basis for some applications. We can find many places using the standard basis. So you can, for example, for Rn, many times you use this standard basis. However, some applications you may find it's better to use other basis, which can give you simple analysis.